Hello students, today we'll discuss about the forces between two parallel current carrying conductors. Under this, the two cases we'll discuss. One is what? If the current in both the conductors are flowing in the same direction. Okay, so see here, we have taken two long straight conductors AB and CD. Through AB, current flowing is what? I1, and through CD, the current flowing is what? I2. Okay, let the distance of separation between them is what? R, smaller. So this is the separation, or you can say distance of separation between the conductor AB and CD. Now, let's first consider the conductor AB, through which current flowing is what? I1. And we know when the current flows through a conductor, a magnetic field is produced all around that conductor. Now, what is the magnitude of this magnetic field due to long strain conductor? So here we'll write here, magnetic field at any point on the conductor CD due to current flowing in the conductor A. Okay, so due to this current which is flowing, due to the current I1, I can mention here, due to the current I1 flowing in the conductor AB. So what will be the magnetic field at a distance R? Because CD is at a distance what? R. And let that magnetic field is represented as B1. Now what is that B1's expression? That is mu naught by 2 pi. Okay, so this is I1, mu naught I1 by 2 pi R. Okay, so this is what? So magnetic field at any point on the conductor CD due to the current flowing in the conductor AB, the expression is what? That is B1 equals to mu naught I1 by 2 pi R. Okay, now if you remember, what will be the pattern of this magnetic field all around this conductor? So the magnetic field pattern will be like this, circular, having common center on the conductor AB itself. So like this you can find. Okay. Now, if you have to find out what is the direction of this magnetic field, so that we can use what? Right hand thumb rule. So here you can see that according to the right hand thumb rule, if you are holding this conductor with your right hand, if the thumb of your right hand is pointing in the direction of the current, then the curl of the finger gives you the direction of what? Magnetic field. So that means at this point, suppose at this point on the conductor CD, we wanted to determine what is the direction of this magnetic field, because the magnitude is this one. This is the magnitude, that is mu naught I by 2 pi R. Now what is the direction of this magnetic field? Because the magnetic field pattern will be looking like this. So at this point, so when you are finding the direction of the magnetic field, as I said, what you have to do, you take your right hand, if the thumb is what showing the direction of the current, then the curl of the finger gives you the direction of the magnetic field. So that means the curl of the finger is pointing like this. So this is the direction of your magnetic field V1, which is pointing into the plane of paper. At this point, let's suppose this is a point O. So at this point, if you are finding the point O is lying on the conductor CD, so at this point O, the magnetic field's direction is what? Into the plane of paper, and it is perpendicular to this conductor CD. It is perpendicular to the conductor CD and it is into the plane of paper. Okay, so this is the B1's expression. So this is, you can say this is B1's expression, this is the magnitude and its direction if you write. So this is perpendicular to CD, conductor CD I can write. So perpendicular to the conductor CD and into the plane of paper. Into the plane of paper. It is moving into the plane of paper. Right? So this is the magnetic field you got. Now, we also know that when a conductor is put in a magnetic field, okay, conductor carrying current, when it is placed in a magnetic field, that conductor experiences a force. Okay, so that means when this conductor CD is what? Inside the magnetic field B1, then this conductor which is carrying current I2, due to that it is also going to experience a force. Now let's find out what is the force experienced by this. So write down here, force experienced by the conductor CD. So here the force is, let me taken as F2. So because it is the CD conductor which is experiencing the force. So this F2, what is the conductor, means that is current carrying conductor. When it is placed in a magnetic field, the force experienced by that, what is the formula? That is BIL sin theta. Right? Now here what is the B? Actually this is the magnetic field of B1 in which the conductor CD is placed. So that's why I'll write this is B1. I is the current through CD conductor, and that is nothing but your I2, and L, the length of the conductor is L, and this is sine theta. Theta is what? That is the angle between the magnetic field and the length of the conductor. And here, as I have already mentioned, this is CD, this is the length of the conductor, and the magnetic field, it is mentioned what? It is making an angle of what? 90 degree. So this is sine 90. Okay, B1 is the magnetic field due to this current I1. So that's this is B1. And in that B1 field, the conductor CD is lying, which is carrying current I2. So that's F2's expression become B1 I2. L is the length of the conductor. And what is the angle between this magnetic field and the length of the conductor? It is 90 degree. So this is the expression. And since sine 90 value equals to 1, so this will become what? This is B1 I2L. Okay, so this is F2. Now here, force per unit length, that will be, let's suppose small f2, which is called as your force per unit length. So that is F2 by L will be equals to what? That will be equals to B1I2. And this B1I2, so let's substitute the B1's expression. Magnitude of B1 is what? Mu naught I1 by 2 pi R into I2. So that is I2. So this is that F2 value. What is F2 actually? F2 is the force per unit length. Okay, force per unit length applied on this conductor CD or experienced by the conductor CD. Now this mu naught I1 I2 by 2 pi R. So this is the magnitude part of this force. Now what is the direction of the force? How to find out? So the magnitude of the force you have got this, but to find the direction you need to apply what? Fleming's left hand rule. And when you can apply this Fleming's left hand rule? If the angle between what? That is the angle between that B and L is 90 degree. In that case you can apply this what? That left hand rule. So let's apply this left hand rule to find the direction. Now what is the statement of this one? Now you have to stretch these three fingers, that is thumb, first finger and the middle finger of your left hand, right? If the first finger projecting or you can directing towards the direction of magnetic field. So look at here. What is the direction of the magnetic field? It is into the plane of paper. So imagine this is into the plane of paper like this. Okay. And this middle finger, it shows the direction of the current flowing. Now here in this conductor, the current is flowing upward like this one. So you can see this first finger pointing into the magnetic field, right? This middle finger pointing in what? Towards the direction of the current flow. Then this thumb gives you the direction of the force. Now here the force direction is this one. So that means at this point, if you look at, this is B1's direction, this is current, and the direction of the force is this one. And this force, as I said, this is F2. The force experienced is what? This is F2. So this is what? What is this direction of this F2? F2, you can see that it is towards the conductor AB. So I can mention this is towards the conductor AB. Okay, towards the conductor AB. Okay, so we have got that expression of what? Force per unit length, which is acting on the conductor CD due to the current flowing through the conductor AB, which is held parallel to it. Now similarly, we can also find out what will be the force experienced by the first conductor, that is AB, due to the current flowing through the second conductor, that is CD. Now magnetic field due to the conductor CD. Due to the conductor CD, let that be taken as what? V2. Okay. Now V2 will be equals to what? The expression is same here like the previous case. The distance of separation between the two conductors as we have taken R. So magnetic field due to the conductor CD at any point on AB. At any point on AB. So will be what? B2 will be equals to mu naught. The current flowing through the conductor CD is I2 by 2 pi R. So this is the magnitude of what? The magnetic field produced due to this conductor CD. And if you have to find out what is the direction of this magnetic field, we have to follow that same right hand thumb rule to find its direction. Now if you apply this right hand thumb rule, now as the statement says, you have to hold this conductor CD with your right hand and the thumb is pointing towards the direction of the current. That means this is the direction of the current. Then this curl of the finger gives you the direction of the magnetic field. So that means the magnetic field is going like this way. So this is the direction. Okay, it is moving like this way. So at this point, this is the direction of this magnetic field. Okay, so this is B2's direction is this one. Okay, let's suppose this is point O dash. So at this point O dash, the direction of magnetic field is what? It is coming out of the plane of paper. And it is also perpendicular to this conductor AB. So that's what you can write. It is perpendicular to conductor AB and coming out of the plane of paper. Out of the plane of paper. Okay, so this is the value of this magnetic field. Now as we know, this conductor AB which is placed in the magnetic field V2, and since it is carrying current I1, so it is going to experience a force. Now what is the magnitude of the force? Let's find out that. So here the force experienced by the conductor AB. Okay, so force experienced by the conductor AB, and let that is taken as what? F1. And what is F1's magnitude? The formula is same, BIL sin theta. So here B is what? B is the B2 value, that is the magnetic field B2 in which the conductor AB is placed. So that's it, this is B2. I is the current which is flowing through the conductor AB, and that is nothing but a I1. And length L is the length of the conductor AB into sine 90 degree, because this magnetic field and the length of the conductor is making an angle how much? This is 90. Now since sine 90 is 1, so this will become what? B2 I1L. Okay, or if I am finding small f1, that is force per unit length, now this will be equals to B2 I1, or that's equals to, if we have to substitute B2's expression over here, so this is mu naught I2 divided by 2 pi r into I1. Okay, so this is mu1 I1 I2 by 2 pi. So if you look at the direction of this force, to find out that, as I said, what Fleming's left hand rule can be used. Now according to this Fleming's left hand rule, this first finger pointing the direction of the magnetic field. If you look at this magnetic field, it is out of the plane of paper. As I said, it is coming out of the plane of paper, right? The middle finger is pointing the direction of the current. The current's direction is upward, right? This is the magnetic field coming out of the plane of paper. This is the direction of the current. Then the force is pointing this. So that means this is the direction of the force. So this is the direction of the force one. So this F1 is towards what? CD. This is towards the conductor what? CD. Now F2 we got, it is towards AB, and we have seen that F1 is what? Towards CD. So that means we have seen that F1 and F2's magnitudes are same. Both are having the magnitude mu1 I1 I2, sorry, mu naught I1 I2 by 2 pi r. Magnitude is same. Only thing is that both are acting in the opposite direction. Okay. So we can write down F1 is equals to minus of F2. That means both the forces are having equal magnitude, but the thing is that both are acting in the opposite direction. That means you can see F1's direction is towards CD, and similarly if you find out for F2, so here F2's direction is what? Towards AB. So both are acting in the opposite direction, and this is, we can see that AB and CD, the forces which is acting in between them is what? Attractive in nature. Okay, so here that means what is the conclusion we have drawn here? When currents in both the conductors, in both the parallel conductors, are in same direction, then force between them is attractive. So force between them is what? Attractive in nature. Now similarly we can show that when the current flowing through both the conductors are in opposite direction. So in that case, forces will be what? In repulsive in nature. So okay, so here under this forces between two parallel current carrying conductors, we are discussing the second case where we have to find out the force between these two conductors when the current flowing them is what? They are in opposite direction. You can see that through the conductor AB, the current is flowing in what? B2A, this direction. And in case of the conductor CD, it is flowing from C to D, just reverse direction of this one. Now we have to find out what will be the magnitude of the force between these two and what will be the direction of the forces is acting between them two. Right? Now let's first consider this conductor AB, due to which we have to find out what is the force experienced by CD. So the same method here. So if we find, so force, magnetic field due to conductor AB at any point on CD. Okay, so here let that be taken as your magnetic field is what? B1. Now what is B1's expression here? So B1 will be equals to what? Mu naught I1 by 2 pi r. Okay, so magnetic field due to a long straight carrying conductor, what is the expression? Mu naught I by 2 pi r. So here in the conductor AB, current flowing is I1 and that's why mu naught I1 by 2 pi r. Okay, now what is the direction of this magnetic field? Perpendicular to CD and into the plane of paper. Okay, so what earlier we have done the same way, right? Now, and CD, the conductor which is carrying current I2, since it is placed in the magnetic field of V1, it is going to experience a force. So let's find out the force here. So force experienced by the conductor CD. So let that force be taken as your F2. Now what is F2's expression? This is small f2, that is force per unit length. Now it will be equals to what? That is F2 by L. So this is equals to B1 I2, right? Now what is B1? That is mu naught. So here mu naught I1 I2 by 2 pi r. So this is the expression of the magnitude of the force experienced by the conductor CD. Okay, the force direction is what? The force direction is what? Away from the conductor AB. So it is away from conductor AB. Okay, so this is what we got this F2's expression. Similarly, we can also find the expression of what? F1. So in this case, again we have to find out what is the force experienced by the conductor AB due to this conductor CD. So the same thing, first we'll consider this conductor CD which is carrying current I2 and we'll find the magnetic field due to that. So magnetic field due to conductor CD, okay, at any point on AB. Okay, so let that magnetic field is taken as what? B2. Now what will be B2's expression? Mu naught I by 2 pi r. So here mu naught I, what is I flowing here? That is I2 through the conductor CD and by 2 pi r. So the direction of the magnetic field is this one. So this is B2's direction. Now what is the direction? It is going into the plane of paper, right? So how it is moving? So it is going into the plane of paper. Into the plane of paper and perpendicular to AB conductor. Okay? Perpendicular to the conductor AB and is moving into the plane of paper. Okay? Now again the same thing, since the conductor AB is placed in this magnetic field and carrying current I1. So in that case this AB conductor is going to experience force. So let's find out the force here. Now force experienced by the conductor AB, and that force will be F1. Okay, Now, or that is same as what? B2 I1L. Or if I am taking this small F1, that is force per unit length, this is F1 by L. Now this will be equals to what? B2 I1. Now if I replace that magnitude of B2, so what the value is? This is mu naught I2 by 2 pi R and into I1. So again we have seen that the magnitude of the force experienced by this conductor AB is coming the same. But to find out the direction, I will use Fleming's left hand rule. This first finger is pointing in the direction of the magnetic field. As I have said, it is going into the plane of paper, right? And this is direction of the current. Okay, direction of the current. Now what is the direction of this force? So the direction of the force is this one. Okay, so this is the direction of this force. So this is F1's direction. So that means we can say that the force which is acting, it is away from the conductor CD. Look at, it is moving away from the conductor CD. So this is away from CD. Okay, when current in both the conductors are in opposite direction, then the force between them is repulsive. It is repulsive in nature. So, definition of Definition of 1 ampere. So we got this force per unit length, F by L. What is the formula we got? So that we got mu naught I1 I2 by 2 pi R. So this is the formula we got. Now if I am taking I1 equals to I2 and that both are taken as what? 1 ampere. Okay, I1 I2 both are taken as 1 ampere. This R, which is the distance of separation between the two parallel conductors, if that is taken as 1 meter, okay, then in that case here force per unit length F by L will be equals to what? That is mu naught by 2 pi. Okay, F by L will be equals to mu naught by 2 pi because I1, I2 and R both I have taken as 1 meter. Now what is mu naught's expression? Mu naught value is what? That is 2 pi into 10 to the power minus 7 divided by 2 pi. 2 pi gets cancelled. So what is this we are getting? This is 10 to the power minus 7. Whose value? This is F by L, and F is what? Force, and this L is the length. So force per unit length value is coming to be 10 to the power minus 7 Newton per meter. Force is Newton, L is meter. Now, okay, so see here the definition of 1 ampere. So 1 ampere is that value of the steady current which are flowing in each of the two parallel infinitely long conductors of negligible area cross section placed at a distance of 1 meter from each other. So like that we used to take two conductors which are infinitely long straight conductors AB and CD. What is the distance of separation? 1 meter. So that means when they are placed in 1 meter distance in vacuum. So that time it is producing what force? Producing a force of 2 into 10 to the power minus 7 Newton per meter length of this conductor. Okay.